Okay, hi everyone. I'm continuing on in my pre-lab lectures here about Lewis structures, and what I want to talk about now is deciding between competing Lewis structures. Right? What happens when I can draw two valid Lewis structures? How do I know which one's right? And I want to give you a specific example. So consider this molecule, hydrogen cyanide, HCN. Take my word for it. It has 10 valence electrons. And if you go through and draw out the Lewis structures, it will turn out that there's actually two possibilities. So one of the possibilities has carbon in the middle, and one of the possibilities has nitrogen in the middle. Both of these structures have 10 valence electrons, and both of them have atoms with satisfied octets. Right? So how do you decide which one is right? Here's the answer. Right? It's called formal charge. So the idea is electrons like to have the same number of valence electrons in the bonded molecule as they do in the isolated atom. And there's a specific formula that you're going to apply in order to calculate formal charge. It's given on page 108 of your lab manual, but here it is. Right? Formal charge is equal to the number of valence electrons in an atom minus the number of unshared electrons minus the number of bonds. So I'm going to go through and draw those two molecules again. Here was one. Here was the other. H, N, C. We're going to go through and calculate formal charge for both of these. Formal charge is associated with each atom. So when you calculate formal charge, you're going to calculate it for each atom in the molecule. And I'm going to write here in red. Wrong thing. Okay, so let's calculate it for hydrogen. Number of valence electrons, formal charge. Right? It has one valence electron. Number of unshared electrons, none. Minus number of bonds, this has one bond. Right? So the hydrogen in this molecule has a formal charge of 0. Carbon. Carbon has 4 valence electrons in the neutral atom. It has no unshared electrons around it. And it has 1, 2, 3, 4 bonds. 4 minus 0 minus 4 is also 0. Last but not least, nitrogen. Nitrogen has 5 valence electrons. It has 2 unshared electrons. It has 1, 2, 3 number of bonds. 5 minus 2 minus 3 is 0. So none of these atoms in this arrangement have any formal charge. Let's compare that over here. If I were to look at hydrogen, again, this will have 0. If I look at nitrogen, again, 5 valence electrons in the neutral atom. It now has 1, 2, 3, 4 bonds. 5 minus 0 minus 4 is plus 1. When you have an instance of formal charge in a Lewis structure, the way you indicate that is by writing the formal charge above the atom and circling it. So when I write plus 1 and circle it, it indicates that this has a formal charge of plus 1. Carbon, 4. This has 2 unshared electrons and 1, 2, 3 bonds. 4 minus 2 minus 3 is negative 1. So we have now calculated formal charge in our atoms. And once we've done that, we can evaluate which molecule is right. Here's how you do that. The structure with the least formal charge will be preferred. And by least formal charge, I mean the least number of instances of it. So what is my right Lewis structure here? Well, on this one, I have 2 instances of formal charge. On this one, I have none. So this is the right Lewis structure for hydrogen cyanide. Right? So structure with the least formal charge will be preferred. Right? You will find out that the total formal charge will equal the charge on the molecule. So if it's neutral, the total charge has to be 0. And you saw that in the structure on the right, +1, -1. Note that if you have an ionic species, there will be at least 1 atom with formal charge. When you have situations where formal charge cannot be avoided, electrons should be arranged so that the formal charge is located on the most electronegative atom, or sometimes on the central atom. So stick it on an electronegative one or on the central atom. And just some rules of thumb, if you have formal charges of -1, that's okay, that happens. Formal charge of -2, maybe, I'm sure there's some examples of it, but I would double check. Formal charge of -3, I have never seen it. Right? If you have a formal charge of -3, you probably need to go back to the drawing board. Okay, there's another issue, which is known as resonance structures. So here's the idea. If multiple equivalent Lewis structures can be drawn for a given molecule, each of these contributes to the overall true structure and lowers the overall energy of the molecule. Let me give you an example. Ozone. Ozone is O3. 6 times 3 is 18. It has 18 valence electrons. If you were to draw the Lewis structure for it, you will end up getting something like this. If you count this out, it will turn out that this one has a formal charge of -1. This atom has a formal charge of +1. This is the correct Lewis structure for ozone. But what you might notice is that I drew the double bond on the right. I could have drawn an equivalent structure with the double bond on the left. That would look like this. Again, +1, -1. These 2 structures are equivalent, right? And they're called resonance structures. It turns out that when you can do that, it's important to indicate it. And the way you do that is with a double-headed arrow. Right? If you see a double-headed arrow that looks like this, this means resonance structure. Right? And you need to draw both resonance structures when you have a Lewis structure. So indicated by the double-headed arrow, only electrons move in a resonance structure. If you're moving nuclei, it's actually considered a different molecule, right, an isomer. And so that doesn't count. Only electrons move in a resonance structure. The true character of the molecule, right, exhibits some character which is in between the component resonance structures. So in that previous example, you might ask if the bonds are exclusively single bond or exclusively double bond in character. And the answer is no, they are not. They're not exclusively single, nor are they double bond. They're sort of 1.5 bond structures. And so sometimes the way you indicate that is as follows. Right? I draw that second one as a dashed line, indicating that it's somewhere between a single and a double bond. And last but not least, not all resonance structures contribute equally to the true structure. You can draw resonance structures which may be so high in energy that they're not contributing to the actual structure and nature. Doesn't often happen. Usually you see structures with high degree of symmetry, but this can happen as well. All right, lecture 2, I'm stopping here. One more and then we'll be done. I hope you like the goggles.